All right, welcome to week 3 of Honors Physics e-learning. For this edition of our notes, uh, with a request from Mr. Evan Gabaldon of Mr. Brooks's first period, we will have some background 80s music for this video set. All right, so this week's topic is freefall. We'll be learning how to analyze an object in a state of free fall while only moving in a single vertical direction. All right. As always, first thing, we're going to watch this video, work through the slide document. Um, by doing this, you'll be able to fully explain what is meant by free fall and include in your explanation why it can occur while an object is moving upward. Uh, then you'll go through your Google form practice week 3, as well as a project that includes 2 activities. You will then be able to master algebraically solving for various quantities, right? Initial velocity, final velocity, displacement, position, or time elapsed during a free fall motion. And lastly, you should be able to create as well as read or infer information from both velocity and position versus time graphs for free fall motion. Okay. Now remember, free fall does not necessarily mean an object is falling. It just means that the only force acting upon an object is its weight, which is what we refer to as the force of gravity. So in this situation, there are no other forces, right? Our air resistance forces are very insignificant, they are near zero. If you look at the little image to the side here, here are 2 different masses, right? A 10 kilogram and 1 kilogram object. The force of gravity is different, right? 100 newtons, the other one's 10 newtons. But if you apply Newton's second law, you'll kind of confirm that each object will accelerate at the same amount, which is what we refer to as the acceleration due to gravity. Right? It's specifically 9.8 meters per second squared on the Earth. We have been rounding it to 10 to make our math easier, and we will do that during this weekly lesson. With us talking about acceleration, this is a good point to just review its definition, right? Remember, its units are meters per second squared. It is the ratio of our change in velocity versus time elapsed. Okay. Sometimes we write this as delta V, meaning final velocity minus initial. We use the subscripts F and I for final and initial. Here is an example of an object being fired upward at 30 meters per second. And once again, this entire motion is in free fall because the only force acting upon it is the force of gravity. Right, so that's why the term free fall is sometimes confusing because an object can be moving upward. In this image, we are assuming 10 meters per second squared down for the acceleration. That's why on the way up, the object loses 10 meters per second of speed each second. Once it reaches its peak at 3 seconds, then the velocity becomes negative, and each second you are continually gaining a downward or negative velocity. So this entire motion would take 7 seconds in the picture. Right? Distances, though, how far an object moves, does not necessarily depend upon how quickly the speed is changing, right? You'll see we had done this earlier in the year that the distance you cover is proportional to the square of the time. Okay, so here delta x stands for your change in position, right? Hence our displacement. VI stands for initial velocity, A is the acceleration, and the T in both locations in the formula here is the elapsed time, right, measured in seconds. So here's an example of using that formula with the situation provided back on slide number 4, right? So in this picture, we didn't have any distances spelled out in the picture. We just have what the velocity is each second. All right. If we wanted to figure out the highest point, in this case, how far is this peak from the launch point, we could use this formula and use the time it takes to get to the peak. All right. So notice we reach a velocity of 0 at the peak. That occurs at 3 seconds. So if we input our initial velocity in time, as well as our acceleration and the time, remember to square this, work through your math, we would figure out then the distance from here, right, up to the peak would be 45 meters. Notice it comes out positive because it has risen to that point. This situation is a little bit harder than what we've done earlier in the year. Here, the object 3 seconds to come up, 3 seconds to come back down to the same position. But say this was on a hill and this was able to fall a further distance, right? It's not perfectly symmetrical. What is this distance of drop here? How far is this point from that point, right? If we go through this, this was 7 seconds. Just use the same formula, input 7 seconds. And if you work through all the math, you'll see that you get a negative answer, which makes sense because the object has dropped from 0 seconds to 7, right? So this hill must be 35 meters tall because it has dropped that amount. Right? If we use the same equation at 6 seconds, right, you can kind of think about this. You should get an answer of 0 because we would be at the same position that we were at 0, right? Try it for yourself. Use this equation and plug in 6 seconds. Now, if we look at our graphing, um, if you take your formula for acceleration and actually write out delta V as Vf minus Vi, if you rearrange that mathematically and solve for final velocity, you see you get an equation that looks eerily similar to an equation of a line, right? So if you were to work through this, you see that the initial velocity is your B value or your y-intercept, and the acceleration is your slope. Okay, this is an interactive Desmos graph. Please click on it, kind of play around with it. You may have to use it later, right, in this week. The position versus time graph, as we had learned, leads to a quadratic equation, which leads to a parabola. So if we take the formula for displacement, but write out delta x in terms of xf minus xi, where xf is your final position and xi is your initial position, we see that we get a generic equation in a quadratic form where the big A coefficient out front is equal to half the acceleration. The B value is equivalent to the initial velocity, and the C value, which is the place that the parabola crosses, right, the y-axis, is just your initial position. If you click on this interactive, you'll be able to specify what the C value is, what the initial velocity is, as well as the acceleration. Make sure you input it as negative because the acceleration due to gravity is downward. If you notice in this one, I put an initial position of 35 because that winds up being the situation on the previous slide. The hill was 35 meters above the ground. Okay, so you can kind of mess around with this one as well and see if you make sense of it. Lastly, here are two interactive practice algebraic problem solving cases. This is not graphical. This is totally algebraic, where the first one has to do with just a straight up free fall drop, right? So there's no launching upward or downward. It's just a drop straight down, okay? The second one, though, involves an upward toss, right, from a rooftop. I have provided embedded video help here of an example working through the two of these, right? So please take the time to work through these before you move on to your practice and then eventually your project.